Hi everyone. Um, I made a video for it's like a makeup video because we couldn't finish the divider in risk 5. Need to explain divider, also a little bit about multiplier. Uh, so we know how to do multiplication in risk 5. So if we multiply 2n bits register, you're gonna have 2n bit result or product. But the method of multiplication, as we explained before, was like adding partial products. So adding these partial products can be done with adder and shifter. As you can see, it gets shift. So we already explained this. We had the algorithm for that, and we also had a data path for that, but this data path is not optimal at all. Need 128-bit ILU. That is a too big ILU, lots of extra circuit, and two registers that are 128 bits registers. Can we do that more optimized? Yes. In another method, instead of having two registers, we can have one. And in this case, actually we can have 164-bit registers just for multiplicand and combine multiplier and product in one register, and when we shift that to right, we do shift both of them at the same time. In this case, you need a kind of circuit that accept two control signals, but it's possible to do that. So we explained this, that as well, but still we need n cycle. If ILU get one cycle, because we are doing a loop, we need n cycle to finish multiplication of 2n-bit registers. Can we do it faster? Sure. How? We can do product. We can do actually parallel add up. So how we can do that? If we multiply, for example, two 4-bit registers, the method was like that. We multiply this by that, 0, 0, whatever, and then result of this. Then after shifting, as we explained, each of these is a partial product. Partial product, and then add them together. That's 2n. Okay, so we had that. But what about we do, instead of adding them together, in this 4-bit, we have one adder for this, one adder for this. Okay, and do another add for the result. This is gonna make a tree structure. As you can see here, we have this tree structure. So we explain how this works. This is very smart design. So instead of having 128 bits adder, we can do it with 64, and we take one extra bit out from right and left. We had example last class, so you can take a look at that. So also we explained that. The last part, it was multiplication in RISC-V. In RISC-V, we have multiple instructions to do multiplication, but the tricky part was that multiplying two 64-bit cannot fit in one register. We need two registers for that. That's why we have different instructions. We have one instruction for lower bit multiplication and three instructions for upper bits. Why three instruction? Because for upper bit we can consider them all signed, all unsigned, or one unsigned, one unsigned, different cases. But mostly these two are enough. Let's see in an example. In an example, imagine we are multiplying two registers, x10 and x11, and we want to put the low register result in x5 and high register in x6. How we can do that? First of all, 2 power 63 means 1 and 63 0, 63 0 and 1 1. This is 64. So this is very big number. If we multiply this by 2, this is 2, this is x10 and this is x11, the result gonna be multiplication of this, the result gonna be 1 and 64 0, that you cannot fit it in one register. Okay, that's why we need two registers. So we need two multiplication, one mul, the result of mul x5, x10 and x11 is gonna be 0, as you can see here is 0, and mul upper bits x11, x10, x6, the multiplication of that is this part. The result gonna be x6 gonna be 1. And if you want to use both cases, you need to consider x6, x5 as a 128-bit register. Okay, so we can use different examples for that. But something that I want to talk about mostly is about dividing, because for your assignment you need to know how we divide. Dividing in computer is exactly similar to the type of dividing that you were doing in high school. It's called longhand division. In longhand division you have a divisor, you have dividend, and the result is a quotient. So normally you are the Q result is equal to actually dividend over divisor, and you might have remainder. If you divide, for example, 1 0 0 1 0 1 0 to this number, the result is 1 0 0 1 and remainder is 1 0, something like that. Okay, so how we can do that? Normally this can happen with subtraction. You consider, because this is 4, you consider 4 bit this one, and you are considering 1 here, because this divider is smaller than this 4-bit is okay. If it's not, you need to put 0 and put another bit down. After subtraction, the result is 1. So the result is 1, but when you put it's not just 1, is like this. When you put this here, the result is negative, so you need to put 0 and bring another one down. Again, the result is negative, you need to put another one down, and when you put in this case the result can be positive and 10. So if you don't know how to divide by hand using longhand division, you need to go and learn it. But this algorithm using the same method. Okay, I'm gonna okay, for subtraction, like for example subtracting this with this, you had that in high school. You can use truth table like that, a minus b, if you have a b in as a input, like a carry. Another way is that you can write this as a 2's complement. This is equal to 2's complement of that. 2's complement of this is equal to, we find a complement plus 1. 1 plus 1 is 10. 1 plus 1 is 10. 1 plus 1 is 10. 1. Okay. And this is equal to this. The result gonna be 1. Adding together, this add to this, and we want to be 1 carry, so the result is carry is this one. So as you can see here is coming from that. Anyway, this is how we do division. If you don't know that, go learn that. This hand division is important for algorithm. Let's go see the algorithm, how it works. In algorithms, what we are doing, the procedure start with subtracting divisor register with reminder. So we do some initialization. The initialization is like that. So let's do initialization with the previous example that we had. So this is divisor. And actually this is like this, and dividend was 1 0 0 1 0 1 0. Okay, so the first thing that we need to do is to make them fit them in registers. So let's see the algorithm here to see the size. So the divisor, even though divisor can be fit, for example, in 64, we need to consider 128, and we put divisor in the highest part. So we do the same way here. So divisor in this example was 1 0 0 0, so we put it in high, and the rest is all 0. Okay, and but reminder can be already 128. Okay, it can already be 128 because we want to divide this. This reminder is actually dividend. So this is actually dividend. So the first initialization is to put dividend inside reminder. So let's put that here and here. So we put 1 0 0 0 0 0 0 0 here, and put dividend, that is 1 0 0 1 0 1 0. We put another one here to make it, for example, in this example, instead of 64, we have just 4. So the remainder is 8 bits, and here is also 8 bits. Okay, so we put another 0 here to make to align the size of these two registers. So the important part you need to consider here is this part. You need to fill the lower part all with 0. And also here highest part with 0 to fit them. So normally reminder need to be like 2 times size of this. If it's not, you need to fill it with 0. Okay, we can have another example. Anyway, let do it to see how it works. So so normally the algorithm is like that. So first we subtract divisor. This is reminder, and this is divisor. We subtract reminder with divisor. If the result is negative, as you can see here is negative result, so we put 0 as a code and shift this divisor to right. So the result is negative. You don't need to compute it. As far as it's negative, you just need to shift this and then again do subtract. This is subtract. I'm not talking about timing here. Timing gonna make it complex. I'm not consider that here. Just explain the data path without considering timing or clock for simplicity. So this one, the result is positive. What is the result? Result is 0, 1, 0, 1, 0, 0, 0, 0, and is bigger than 0. So in this case, the quote is 1. Okay, the quotient is 1, and we shift. Now we do another shift. Anytime we shift, 1 0 gonna get disappear here, and another 0 gonna come here. Okay, now we do again subtraction. 0 0 1 0 0 0 0 0. So the result is negative. So we put 1 0 here. We shift another one. It's gonna be here. You don't need to keep computing the subtraction. Again, this one, if we put it here, is bigger than this. Result gonna be negative. We put another 0 here. We shift another one. Now we can do subtraction because the result is not negative anymore. So the result is this 0 0 0 0 0 0, and this is bigger than 0. We put 1, and as you can see here become all 0. We kind of shifting divisor from this highest bits to the lowest bits, and we are done. We repeated 4 times in this case, and this is reminder, and this is the Q. So we have quotient and reminder. So this is how the algorithm works. For your actually assignment, you need to optimize this. Instead of having 128 bits, you can consider divisor fixed register without shifting and put a big reminder and put the ILU instead of 128 bits, just 64, similar to what we had for multiplication, optimized multiplication. Okay, I wanted to explain this. Yeah, next class we're going to talk about floating point. Okay, have a good day.